You're welcome to another edition of online lectures for anatomy and physiology for the community health students of Faculty's College of Health Science and Technology. This is specifically for the 100 level. Like I said earlier in our previous lecture, I said this is just a palliative lecture that we could use to keep ourselves abreast of our curriculum while we are home on a lockdown. I hope you're all staying home and you're staying safe. To ensure that this lecture series continues, I want you to hit the subscribe button that you can find on there where they wrote subscribe. Just hit the subscribe button and you'll see a bell very close to it. That's a notification sign. Also hit the notification. This allows you to get a frequent information anytime I release my lectures online, just in case you might not be able to get the link. Once you get the notification pop on your phone, you can always go and listen to the lecture over and over again. Please take note that even our previous lectures, I'm planning to do something about them to make sure that you have them online to enable your reading as you go on. Today we'll be talking about the cardiovascular system. Very interesting system, and I want you to sit tight and take your lecture series, this lecture series very importantly, and I'm sure you'll have a great time watching this. Let's talk about the cardiovascular system today. The cardiovascular system. The cardiovascular system is part of the circulatory system. The circulatory system is divided basically into two parts: the cardiovascular system and the lymphatic system. The lymphatic system is composed of the lymph vessels, the lymph nodes, and other lymph organs. However, the cardiovascular system, as the name implies, cardio and vascular, is made up of the heart and the blood vessels. Cardio implies heart, vascular system implied a network of blood vessels. The heart has a pumping action that ensures constant circulation of blood. However, the blood vessels form a lengthy network through which this blood flows. The whole idea of the cardiovascular system is to ensure that blood that is needed, or nutrients and oxygen that is needed for metabolic activities, gets to the tissues through the blood. As much as the heart pumps the blood vessels ensure that this network allows the blood to reach these tissues and the tiny cells. The heart pumps blood into three anatomically separate systems of blood vessels. This is the pulmonary circulation. Pulmonary circulation has to do with the point where blood, the right side of the heart, pumps blood to the lungs for reoxygenation, or in the case of deoxygenated blood, it goes there for a reoxygenation. The second is the systemic circulation. The cardiovascular system ensures a continuous flow of blood to all body cells, and its function is subject to continual physiological adjustment to maintain an adequate blood supply. If the supply of oxygen and nutrients to the body cells becomes inadequate, tissue damages occur and cell death may follow. Hence, the systemic circulation ensures that blood reaches every body cell, and the left side of the heart is responsible for pumping blood into the systemic circulation. The coronary circulation has to do with the blood supply and venous drainage of the heart's tissue itself. As a heart is part of a living organism, it's composed of cells, and its own cells ought to have metabolic processes that occur. They need supply of oxygen, they need supply of nutrients, and everything that the normal cell also needs. Considering the need, therefore, about 5% of the cardiac output goes into the coronary circulation. This picture represents the alveolar sacs where the right side of the heart pumps blood into. The right side of the heart pumps deoxygenated blood into the lungs. Now, upon reaching the lungs, this deoxygenated blood gets into the alveolar sacs, as you can see. The alveolar sacs contain inhaled oxygen. Now, this deoxygenated blood contains a lot of carbon dioxide compared to the low partial pressure of oxygen. And because of the process of facilitated diffusion, The carbon dioxide in this blood get exchanged for oxygen that is present in the lungs. Now the blood becomes oxygenated and gets through to the arteries, depicted as red, and move all through the pulmonary vein down back to the heart. This is the process by which blood coming from the body and tissue waste is being reoxygenated. When carbon dioxide comes from the pulmonary artery into the alveolar sacs, this carbon dioxide has been exchanged for oxygen. This same carbon dioxide follows through the bronchioles and then to the trachea and out of the body through the nose or the mouth, as the case may be. Systemic circulation has to do with pumping blood to the left through the left side of the heart to supply every cell of the body, as we have earlier discussed. Let's look at the location of the heart. The heart is located in the thoracic cavity, or rather say the chest cavity. The heart is located at the left side of the thoracic cavity. Specifically or anatomically, the heart is located within the second to the fifth intercostal vertebra. The base of the heart coincides with the second intercostal space, whereas the apex of the heart coincides with the fifth left intercostal space. Just a little bit lateral to the sternum is where you have the location of the heart on the left side. The base is directed upwards and the apex is directed downwards. The apex of the heart has significance in the sense that the maximum heartbeat is felt at the apex of the heart. In the cases of an applied anatomy, when the apex of the heart or the maximum heartbeat is felt anywhere else other than the fifth left intercostal space, it actually depicts either an enlargement of the heart or a reduction in the size of the heart. For example, when the apex of the heart, instead of being at the fifth left intercostal space, mid-clavicular line, is then found in the sixth left intercostal space, anterior axillary line, the condition is called cardiomegaly, meaning that the heart has actually increased in size, so much more that the apex has gotten to the sixth left intercostal space. What does the heart look like? The heart is a roughly cone-shaped muscular organ. It measures about 10 centimeters, about the size of a clench of the fist of the owner, 10 centimeters in length. The weight of the heart differs for men and women. It's very obvious that the general weight of a man is higher than that of a woman. And so, if the general weight of a man is higher than that of a woman, it is expected that the size of a heart will weigh more in men compared to that of women. It may also be recalled also that the volume of blood in a man is more than that of a woman. As such, the size of the heart of a man will weigh more than that of a woman. So as seen in the picture represented, the weight of the heart in a woman, it's about 225 grams in a 70 kg in an adult woman, whereas it weighs about 310 grams averagely in an adult male. Let's look at the parts of the heart. This is an animation that actually represents the different anatomical parts of the heart. The arrows you can see there represent the direction of blood flow. The heart is made up of 4 chambers: the left atrium, the right atrium, the right ventricle, and the left ventricle. Please let's take note that the heart is divided into 2 parts, left and right, by what we call a septum. This septum divides the heart into the left side and the right side. Let's also take note that the left side has to do with pumping of blood into the systemic circulation, whereas the right side has to do with pumping of blood into the pulmonary circulation. The blue painted organs seen there as part of the heart represent areas where you have some level of deoxygenated blood. Like your superior vena cava is this way. Then you have this other blue coming up here. It's called the inferior vena cava. Now we have the aorta that takes blood away to the systemic circulation, and we have the pulmonary artery here that takes blood down to the pulmonary circulation. When this blood has been reoxygenated, we have the pulmonary veins that bring blood from the lungs down into the left atrium. If you look carefully here also, you may also see that there are some valves in the heart that divides it into 4 different chambers. We'll look later at the respective valves of the heart. The heart is composed of 3 layers of tissues. Generally, the heart is asymmetrical as a result of the fact that the distance by which blood must travel into the pulmonary circuit and systemic circuits are different. Since the right side of the heart sends blood to the pulmonary circulation or the pulmonary circuit, the distance between the heart and the lungs is quite shorter compared to that which sends that area, that side of the heart, which is the left side, which sends blood to the systemic circulation. Hence, it is important to note that the layer of tissue or the layer or the thickness of the left side of the heart appears to be more because it will be exposed to greater workload compared to the thickness of the walls of the right side of the heart. Anatomically, the heart is composed of 3 layers of tissue. We have the pericardium, which is the outermost layer. We have the myocardium, which is the middle layer, and we have the endocardium, which is the innermost layer of the heart. Let's take a look very closely at the pericardium. The pericardium is composed of 2 layers of pericardial sac. First, the outermost fibrous pericardium, and secondly, the inner serous pericardium. The pericardium is the outermost layer and is made up of 2 sacs, like we said. The outermost layer is a fibrous tissue, whereas the innermost layer here composes of a double membrane or double serous membrane. Now, looking carefully at the anatomy of the pericardium, the outermost layer as depicted in this diagram is the fibrous pericardium, otherwise made up of fibrous tissue. The inner layer there of this pericardium is made up of a fold or a double layer that we call the serous pericardium. This serous pericardium is further divided into 2 parts. The one on the distal portion here is called the parietal layer of the serous pericardium, whereas the one in the proximal portion here is called the visceral layer of the serous pericardium. Another name for the visceral layer is called the epicardium. The myocardium is the muscle tissue, that's the middle layer. It's the muscle tissue, as we all know that the heart is made up of specialized muscles called the cardiac muscles. And these cardiac muscles are specialized in that they are found only in the heart. It is striated just like you have in a skeletal muscle, but the difference is that it's not under any form of voluntary control. Each fiber of a cardiac muscle has a nucleus and 1 or more branches. The ends of the cells and their branches are in very close contact with the ends and branches of the adjacent cells. This closeness makes it to have a symmetry through which the beats at almost the same time. When an impulse is initiated, it spreads from cell to cell through the branches and the intercalated disc over the whole sheet of muscles, and this causes contraction. This sheet arrangement of these muscle fibers enables the atrium and the ventricles to contract in a coordinated and efficient manner. The myocardium is thickest at the ventricle, especially at the left ventricle, because it has the greatest workload, just like we have explained earlier. Looking very closely at this diagram, we could see that the thickness of the myocardium here was picked from the left ventricle. You can see the layers of muscles and the cells, how they are so closely laced together, such that when there's an action potential there, it causes it to beat almost at the same symmetry. The next is the endocardium. Endocardium is the innermost layer of the heart. This endocardium is seen to be very smooth, thin, in order to ensure a smooth flow of blood through the heart. Endocardium lines the chambers and the valves of the heart directly. This endocardium consists of flattened epithelial cells, and it is continuous with the endothelium that lines the blood vessels that you find in the general circulation. Let's look a bit at the coronary circulation. Like we said earlier, the coronary circulation has to do with blood supply to the heart itself. Since the heart is composed of cells, it requires oxygen, nutrients, and energy that is needed for its metabolic processes. As such, there should be an arterial supply to the heart, and there should be a venous drainage from the heart. About 5% of the cardiac output moves into the coronary arteries. Now, this large blood supply goes from the left ventricle. It highlights the importance of the heart to the body function. Now, the heart is supplied by two arteries, like you can see in the diagram here, which is the branch of the aorta, the right coronary artery, and the left coronary artery. And these are immediately distal to the aortic valve. The coronary arteries traverse the heart in the transverse like this, and eventually forms a network of capillaries, like you can see distributed down. The venous drainage is through the cardiac veins that are present on the heart muscle itself. These cardiac veins come together, drain into what we call the great cardiac vein, and at the end of the day, they form what you call the coronary sinus. Away from the coronary circulation, let's talk about the valves of the heart. As we have explained earlier, the heart has 4 chambers. Irrespective of the fact that we've said it has a right side and a left side that is divided by a septum. Please take note that the heart has 4 chambers. On the uppermost part, we have the atria. For singular is the atrium, the right atrium and the left atrium. On the lower part, we have the right ventricle and the left ventricle. But what brings up the separation between the right ventricle and the left and the right atrium, the left ventricle and the left atrium? Looking at the left side of the heart, these valves are made up of a double sheet of an endocardium. These double folds of endocardium is usually strengthened by a fibrous tissue, and it makes up the heart. Now, when I say when I say there's a double fold of endocardial tissue, that fold that we have is called a cusp. When you have one cusp, we have 2 cusps, or we have 3 cusps. In the left side of the heart, it is discovered there are 2 cusps, one here and another here. When you take a closer look at this, you can see this is a cusp and this is another cusp. On the left side of the heart, because we have 2 cusps, what we say to have had there is what? A bicuspid valve. If you look at the right side of the heart, there are 3 cusps that divides the right atrium from the right ventricle. We might be able to appreciate it by the papillary muscles here that holds these valves in place. We have one cusp here, two cusp here, and the third cusp here, making it a tricuspid. Thus, the name is what? A tricuspid valve. So what divides the right atrium from the right ventricle is a tricuspid valve. What divides the left atrium from the left ventricle is a bicuspid valve, otherwise known as mitral valve. Now when we come to the aorta here, this is the pulmonary artery and this is the aorta. The aorta is here and the pulmonary artery is here. At this pulmonary artery here and aorta here, there are cusps that forms the valve. These cusps are semilunar in shape. This semilunar cusp forms the valve that leads into the pulmonary artery and into the aorta itself. So they are otherwise known as semilunar valves. But to be very specific, this particular valve collectively that leads into the pulmonary artery is called the pulmonary valve. That which leads into the aorta is called the aortic valve. Please also note that the same semilunar valves also are present when you have the pulmonary vein coming into the left atrium and the inferior and superior vena cava coming into the right atrium. So when you hear semilunar valves, we are talking of the aortic valve, pulmonary valve, and the valves leading the inferior vena cava and the superior vena cava, then that's leading the pulmonary vein into the heart. The bicuspid and the tricuspid valve are otherwise known as the atrioventricular valve. In the course of this study, we'll refer them to as the AV valves. Now let's look very closely again to a very clearer picture of what these valves look like. This is the bicuspid valve having two cusps, the tricuspid valve having three cusps. Then these are the aortic valve and the pulmonary valve made up of semilunar structures. So they may also be referred to as the semilunar valves. How does then blood flow through the heart? The two largest veins of the body, the superior vena cava and the inferior vena cava, starts the process by emptying waste or tissue waste or carbon dioxide that it has gotten from the systemic circulation. Now, when cells have carried out their metabolic activities, we know that they disperse carbon dioxide as a tissue waste. They also disperse other tissue waste and nutrients that needs reorganization. Now, when this gas gets into the circulation, they are received from the smaller veins into a large vein called the inferior vena cava and the superior vena cava. The inferior vena cava actually picks blood from the lower part of the heart, like you can see this arrow going up. The inferior vena cava picks blood from the lower part of the body at points that are lower than the level of the heart. Whereas the superior vena cava here picks blood from areas that are higher than the level of the heart. So when you talk about blood coming from the upper limb, from the head, from the shoulder, from areas that are above the level of the heart, they drain into the superior vena cava. Then blood coming from areas below the level of the heart drain into the inferior vena cava. Now a combination of the superior vena cava and blood coming from the inferior vena cava enters into the right atrium. Now when blood enters into the right atrium, it moves down here through the tricuspid valve into the right ventricle. From the right ventricle, you follow the arrow, this blood moves to the pulmonary artery. The pulmonary artery then takes blood directly into the lungs for a reoxygenation, like we have earlier said. At the lungs, there's an exchange of gases. That is, this carbon dioxide, which is there already in the blood, get exchanged for oxygen, which is already in the alveolar sacs, by a process of facilitated diffusion. When that oxygen now gets back into the blood, it now comes in through that network and passes through to the pulmonary vein. This pulmonary vein now carries this oxygenated blood down into the left atrium. From the left atrium, the blood moves through the mitral valve or the bicuspid valve into the left ventricle. From the left ventricle, this blood now pushes out through the aorta and moves into the systemic circulation. Now, how does this thing happen in a split second? The atrium, both the right atrium and the left atrium, tend to beat at the same time. Irrespective of the way I have described the movement of this blood, the right atrium and the left atrium beats at the same time. The right ventricle and the left ventricle tend to beat at the same time. First, as blood is getting into the right atrium from the systemic circulation, at the same time, blood gets into the left atrium from the pulmonary circulation. Such, both the right atrium and the left atrium are receiving blood at the same time. The process whereby the right atrium and the left atrium are opening up to receive blood at the same time is called the diastole. Now, when they receive that blood moves into the left atrium, left ventricle and the right ventricle. When that blood gets into the right ventricle and the left ventricle, the next thing is that these ventricles have a function of pushing this blood to the systemic circulation and the pulmonary circulation respectively. Now, please let's take note of these valves. As soon as blood comes from your pulmonary vein and your systemic circulation into the right atrium and the left atrium, the AV valves remain closed, which is your tricuspid, and your bicuspid valve remains closed, in order for blood to come in from the systemic circulation and the pulmonary circulation. After some time, the blood in the atrium gets filled up, pressure builds, and there is a closure of your semilunar valves. Please remember we said semilunar valves are those valves that come from the vena cavas and the pulmonary vein. So, there is a closure of the semilunar valves. There's a closure of the semilunar valves at that point. Now, when you have the semilunar valves closed, blood now gushes out downwards from the atrium down to the ventricle. At this point, the ventricle relaxes as the atrium contracts. That point is called a diastole. Where the ventricle relaxes, the atrium contracts to push blood from the ventricle down, from the atrium down to the ventricle is called a diastole. That means the ventricle is opening up to receiving the blood. Ventricular diastole. As soon as this blood builds up in the ventricle, it gets to a capacity that is filled up. There is now closure of your AV valves and opening of the semilunar valves. Once there's a closure of your AV valves, pressure built inside the ventricles allow the ventricle to contract forcefully to push blood out into the systemic circulation and the pulmonary circulation. Now, when the ventricle contracts at that point to push blood into the systemic and pulmonary circulation at the same time, that part is called the systole. Now, what do we pick out from this? Systole happens when there is a closure of these AV valves, because it's at the point of the closure of these AV valves that blood moves into the systemic circulation or the pulmonary circulation. And when there's a closure of the semilunar valves, it implies that blood moves from the atrium down to the ventricle. However, in a nutshell, we would say that the first heart sound is formed by the closure of the AV valves at systole, whereas the second heart sound is formed by the closure of the semilunar valves at diastole. Let's briefly go into the conductive system of the heart. The heart possesses the property of autorhythmicity, meaning that it has the ability to generate its own electrical impulses and beat on its own. It does not depend on any hormonal control or any nervous control. However, it should be noted that the heart can be supplied by the sympathetic and parasympathetic nerve fibers, which increases or decreases due to the condition that it may be exposed to. The components of the conductive system of the heart is the SA node, otherwise known as the sinoatrial node, the AV node, otherwise known as the atrioventricular node, the AV bundle of the bundle of His, otherwise known as the atrioventricular bundle, then ends up with the Purkinje fibers. The SA node, like we can see depicted on the diagram here, is a small mass of specialized cells in the walls of the right atrium, near the opening of the superior vena cava. It is spindle-shaped and it composes of a fibrous tissue matrix that has closely packed cells. The length is about 10 to 20 millimeters long or thereabout, and it's about 2 to 3 millimeters wide, 10 to 20 millimeters long and 2 to 3 millimeters wide. These sinoatrial cells generate regular impulses mainly because they are electrically unstable. As a matter of fact, it is this instability that leads them to discharge regularly. Or would I use the word depolarize? They discharge because of their instability, they depolarize regularly, usually between 60 to 80 times in a minute. This depolarization is followed by a recovery, and that recovery is called repolarization. But almost immediately, this instability leads them to discharge again. So the more they discharge, the more they recover from it, then they discharge again. And this process of depolarizing and repolarizing sets up the heart rate. Because the SA node discharges faster than any other part of the heart, it is normally referred to as the pacemaker of the heart. It is the firing of this SA node that triggers atrial contraction. Let's talk about the next bundle that you have there, which is the AV node or the atrioventricular node. It's also a small mass of neuromuscular tissue that is situated in the walls of the atrial septum, just near the AV valves here, still on the right side. Normally, the AV node merely transmits electrical signals from the atria to the ventricles. There is a delay here just of about 0.1 second before that signal moves into the ventricles. This allows the atrium to finish contracting before the ventricles start contracting. The AV node also has a secondary pacemaker function that takes over this role. And because the AV node doesn't have as much charge as the SA node itself, it beats at a slower rate of about 40 to 60 beats per minute. Let's go to the next one, which is the AV bundle or the bundle of His. If you can look at it here, is a bundle here just very close to the ventricular septum. It's a structure that connects with the distal AV node here and crosses the fibrous ring that separates the atria and the ventricles, then at the upper end of the ventricular septum here. And this divides into right and left bundle branch, like you have seen labeled here. So that part there, we call it the bundle of His. Now, these right and left bundle branches continue to break up into smaller fibers that we call the Purkinje fibers. First, in the conductive system of the heart, we'll remember that there's an SA node, there is an AV node, there's an AV bundle, and there is Purkinje fibers. The charge is highest at the SA node and begins to reduce till it gets to the AV node, reduces till it gets to the AV bundle, and then spreads these charges over the walls of the ventricles at the Purkinje fibers. I hope we have been able to learn something about the cardiovascular system. Thank you very much for watching. Well, thank you very much for your time and for watching those lectures, and I hope you've gained immensely from that lecture. The cardiovascular system is a very interesting system that you need to learn to read and read and read over again to have a good grasp of how your physiology works. I will implore you to go watch, listen again and again and again on it. Now, I want you to hit the subscribe button on there so that you can get regular notifications on when I release my lectures. Instead of sending the link again, hit on the subscribe button once, and that will also tell how many of you have actually been watching these lectures. Have a wonderful day ahead. Have a great day too.